We are going to see the single stage amplifier today. So for single stage amplifier, we are going to start with common source. So first we will see the common source with resistive load. First, why we need amplifier? So we need amplifier to amplify the low voltage signal to high voltage signal, right? So here we are having the uh, a common source amplifier with resistive load. As we can see, we are applying the input voltage at the gate, taking the output from the drain. Okay, so here source is common, and we are applied here one resistor, and we are giving the here the VDD like 1 volt, 900 millivolt. So as we can see here, what will be the AC small signal gain, and what will be the region of operation, and uh, the large signal region of operation, and the input output characteristics of the single stage amplifier. So so as we can see here, if we are increasing the V in, right? So as we increasing the V in, our this drain voltage will decrease, and the explanation is here. So when we start increasing the V in, right? Let me draw here. Wait 1 second. So when we start the V in from 0, M1 will be off, right? M1 is a NMOS, okay, and V out remain at VDD. Since no current is flowing, so there is no drop across the resistor, and hence the output voltage at the VDD voltage, right? So when we are increasing the V in, when it will reach near to the VTS, that is the threshold voltage, right? The channel charge inversion will be happen, and then NMOS will start conducting, and current will be flow through the channel. So at this point, when begin to conduct the current, and then if there is a small amount of current will flow, then there will be some voltage drop across the load resistance, that is we can say RL or RD, okay, and because of that our V out will be start to decrease, right? So when V in increase reaches to Vth, M1 will be turned on, and V out will be start to decrease, right? So let me show you the curve here, how it is going to be. So you are seeing this red curve, like this is the V out, and here as we can see here, when the V in is small, uh, the this is the region of operation for MOSFET. So we can see in this region, okay, here it is in cutoff, here is in substitute saturation region, and then here it is in saturation region, and then here it is in linear. So we can see here, when the MOSFET is in subset saturation region or in cutoff region, our output will be VDD, right? And as we are increasing the input voltage, our output will start to decrease, okay, right? And this, so the region of operation, this is the region of operation for MOSFET. So we can see between the voltage 320 millivolt to 750 millivolt, our MOSFET is in saturation region. So in this voltage region, we are going to use this structure as a amplifier, because the device to be used as an amplifier, it should be in saturation region. Okay, and this last curve that we are going to see, last one, it is just a derivative of this input output characteristic, just dv out upon my dv in, and that will be gain. Okay, so uh, now let's move to the small signal analysis of that, right? So as we can see that this is the gate, there we have applied the voltage v in, okay, and because of this v in, we are current will be generated, since this MOSFET is a voltage control current source. So when we will apply the voltage at the gate terminal, their current will be generated, that is flow through the drain, and then this is a small signal model where we can show the device modeling like this. And this is due to the body effect. Because of the body voltage, we have GMB and VBS. This is the resistor in the saturation R naught, and this is the load resistor. We can see RD or RL, and we are taking output from the drain, right? So how we will find the gain? The gain we will find like uh, whatever the current, this is GM into V in, this is going through the R naught parallel to RL. So the current going through the R naught parallel to RL into this resistance will give the output, right? So what is V out? V out will be minus GM time into R naught parallel to RL into V in, and gain will be V out upon V in, that is minus GM into R naught parallel to R, right? So here I am not considering this body effect because our body is connected with the source, as we can see here. Here I have connected body. Okay, this is the body terminal with the source. So here the body to source voltage is zero. That's why we are not considering this current source, because if the voltage will be zero, this will be act as a open circuit, right? So okay, so what will be the disadvantage of this circuit? How the large signal voltage change and the input voltage change will affect the GM of the circuit. So the main disadvantage of this circuit is like as we can see here, the gain is dependent upon the GM. Like as in an analog design, we try to make the voltage amplifier such that its gain should not be dependent on the GM. We do like this because if you see here in the circuit diagram, if this voltage is increasing or decreasing, right, this current through this is increasing or decreasing, and the current that is flowing into drain, right, divided by the input voltage, this is the transconductance of the transistor, that is GM. So by changing this VG, this is the input voltage, our current in the drain is also changing, and hence our GM is changing. So we try to make the analog circuit such that it is less dependent upon the GM. Like gain should be less dependent of GM, because when the GM will change upon changing the input voltage, then our gain will change, and then there will be non-linearity between the input voltage and the that current, and because of that there will be the non-linearity of the gain. So here it's mentioned that if the circuit send the large signal input swing, the GM itself vary with the input signal, and the gain of the circuit changes. Okay, if the signal is large, as I have told you. So because of that, the gain of the circuit is vary with the signal swing, and then circuit operates in the large signal model. And the dependence of the gain upon the signal level lead to non-linearity. Right. So we don't want the gain to be dependent on the GM. So what we do, then we move. We want to build a new structure such that this gain is independent of the transconductance. GM we call as a transconductance, right? Uh, okay. So one other disadvantage of this circuit is like this. As we know, the AV is minus GM into RD, or we can say that minus GM into RL. Okay, or we can say that minus GM into RD parallel to R naught, where R naught is the uh, this R naught is the on resistance of the transistor that is in saturation region. So since we are neglecting here channel length modulation, as we know channel length modulation, so we are making this intrinsic that resistor, that is R naught, equal to very very large, and hence R naught parallel to RL is equal to RL, since RL is smaller than R naught. Right. So here uh, the gain AV equal to, as we know GM, we can write like this, under root of 2 Newton's UXW by L into ID. And what is RD? RD is just like a VRD divided by ID, like V equal to IR. If you want to find R, V by I. Then see here ID and ID, we will proceed like this: minus root of 2 Newman cox w by l vrd root of id. So what will happen here? How we are going to increase the gain of the circuit? If we want to increase the gain of circuit, how we will proceed? Like we will going to always in analog design, we going to change one parameter and we are going to keep the other parameter constant, so that we can analyze the circuit easily. If we will going to change more than one parameter at a time, and then it will be difficult for us to analyze the circuit, like the behavior of the circuit. So here we are going like we are keeping all the parameter constant and we are varying only a single parameter at a time, right? So here we are varying, like suppose if I want to increase the gain, then we can increase by three process here. Either we will vary w, we will increase w by keeping this all constant id and vrd, or we will increase the voltage across the resistor, that is vrd, or we will decrease the current, like. So we are going to vary only one parameter at a time by keeping all parameter constant. So like if we want to increase the gain, we will increase the w. So if w is increased, then what will happen? Then parasitic capacitance, okay, will also increases, and that is not the good for our device, as parasitic capacitance will increase, the delay and all will increase, the pole will get affected and all. So this w we cannot increase like too large. Okay, now if we want to keep this w constant and id constant, and we want to increase the vrd. So if we increase the vrd, as we can see here, what is the v out? Here we can see this v out is nothing but this is vdd minus vrd, or we can say vdd minus id into rd, right? So if we will increase this vrd voltage across this resistor, then our output voltage will decrease. So the swing of this circuit, okay, will going to reduce, right? The swing of this circuit is going to reduce because and the voltage at output will be vdd minus I time into rd. So that's why we are not going to increase this vrd. Okay, it is limit the voltage swing. Now what we are going to do, we are going to increase, okay, we are going to decrease vrd by keeping all w and vrd is constant, right? So if we will going to decrease this rd, our gain will be increased. But the disadvantage of this is when we will increase this, when we will decrease this id, okay, we have to increase the rd such that the vrd will be constant, because we are changing only one parameter here and keeping all parameter constant. So if to keep vrd constant, if we will increase id, we have to if we will decrease id, we have to increase the rd. Okay, so if brd remain constant and if id is reduced, then rd must increase, right? Since v equal to ir from there. So if rd will be increased, our pole location will get affected. Okay, and like earlier when rd is less, then pole location will be 1 divided by rd into cl, right? When we will increase the rd, the pole become more and more dominant and it will move near to the less frequency, right? And because of that, our time response of the circuit will get affected. Okay, and the more it will move near to the origin, our circuit take more time to settle down, right? So because of this, we need the greater time constant at the output node. So we are not going to decrease rd, sorry, we are not going to decrease id. So this is the limitation of this circuit. The first limitation is the gain is dependent on the transconductance, and the second limitation is uh, mm, and the second limitation is this uh, to increase the gain, we are bounded so that we cannot increase the gain to a means some certain level, right? So we are going to modify the circuit. What we are going to do, to get rid of gain dependent on the GM, we are using this diode connected load. We have removed the resistive load from here, and we are connected one diode connected here MOSFET. This is the PMOS, this is the NMOS, right? So this is the structure for that. This is the VD, that is 900 millivolt, and we are going to see here also the region of operation of this NMOS. Since this is connected, okay, drain is connected to the gate, it will be in saturation region. We are going to see the region of operation for this NMOS, and we are going to see how the input and output is going to vary by varying the input, right? Like previous case. So this is the upper one, that is V out. This is green one. This is the input output variation. When we are increasing the input in the x-axis, we are going to see the output variation in the y-axis, and the red one is the region of operation for the NMOS, right? So as we can see, when we are increasing the voltage at the input, first our transistor will be in cutoff region, then it will go into the sub-threshold region, right? Then it will go to the saturation, and then it will go to the linear. So we trying to for any MOSFET, for any structure to be work as amplifier, the transistor inside it or device inside it should be in saturation region. So as we can see, this is the region of operation for us, like 340 to 560, right? So this will be the region of operation. In this region only we are going to use this device as a amplifier, right? So what will be the gain of this circuit? Okay, what will be the gain of the this circuit? So let me find from here. For finding the gain, what we do, right? We deactivate the DC source. We only apply the AC source. Okay, we replace the ideal current source or ideal voltage source with its intrinsic impedance. Like for ideal current source, it will be open circuited, and ideal voltage source, it will be short circuited. So here we are applying the a small signal voltage, that is V in. We can see here the AC voltage. So if we see the resistance by seeing upside, like from here upside, so we will find the resistance here by saying up 1 by GM, right? Since it drain and gate is connected, and we are saying at the drain, the impedance by looking the drain of the upper transistor will be 1 by GM. Okay, and what will be the gain? The gain will be minus GM time RD. So we can see here the gain will be minus GM1, if it is, if we are considering this is 1, so minus GM1 divided by GM2, right? So yeah, so here gain will be minus GM1 divided by GM2. Yeah, so what will be gain here? Gain will be the minus GM1, or we can say GMN, this is NMOS, divided by GMP. Okay, then we have, like, what is the transconductance equation? Root of 2 nu n cox w by L into id. Since both in our series, so this id will be same, like, and we keep generally. Okay, as we know that this PMOS is like the moment of the hole is not that much as electron. So for low technology, we can keep uh, like nu n nearly equal to nu p. But in theory, if we study in book, we keep like nu n approximately equal to 2 nu p. So here, if you see uh, here, So what will be the AB? AB equal to nu n divided by nu p into WL by WL of 1 and W by L of 2. So we can see that now the gain is not dependent. Now this gain is not dependent upon the GM, right? This gain is dependent upon the W by L. So our first disadvantage of resistor as a load, that where the gain was dependent upon the RD, like sorry, gain was dependent upon the GM. Okay, like we can see this was the structure, common source with resistor as a load. So here what is AV? AV will be equal to minus GM time RD. So here gain is dependent upon the GM. So here we can see the gain is not dependent upon the GM. So our nonlinearity in the circuit will not here we cannot see observe. And let me zoom this. And here we can see the amplifier gain is not a function of the bias current. So the change in the input and the output level does not affect the gain, and the amplifier become more linear, right? The amplifier gain is not the function of input signal, and the amplifier gain is weak function of transistor size, that is W by L. So we have to change the dimension by considerable amount so that to increase the gain, right? So here to improve the gain, we have to tweak the width of the both transistor PMOS and the NMOS. Now we are going to move to the other uh, single stage amplifier, that is common source stage with current source load. So earlier initially first we have kept here RD as a load, then we have removed that RD with diode connected. Okay, then what we are using this as a current source. This MOSFET is in saturation. We will keep the VB so that MOSFET will be in saturation, right? Okay, we cannot write on this. Okay, and as we know that the MOSFET will be in saturation, act as a current source, right? And here what we will do, we will vary this voltage V in, and we will see the characterizes output voltage, how it is going to behave with the input voltage, and we will going to see the gain and region of operation for this circuit and the uh, output swing. Yeah, please let me know if it is fast. Okay, so we will see here. So as we are seeing here, as the input voltage is increasing, how our output voltage is going to look like. Okay, so on increasing the input voltage, first when input voltage is 0, right, this NMOS will be off, and there will be no current will follow, and then V out will be VDD. Now when we are going to increase the input voltage, the voltage at the drain will going to decreases, right? And we can see slightly this voltage at the drain will going to decrease. Now we can see here, like between 413 millivolt and 433 millivolt, our both the PMOS and NMOS is in saturation region. So we will going to use this device in saturation region as a amplifier. So both PMOS and NMOS will be in like saturation region for this voltage range, right? It is like 517 millivolt to 38 sorry, 517.2, and this between this we are going to use as a amplifier. So as we can see the region of operation for the NMOS, right? The first stage is like same, it is in cutoff, then it will be in substitute region, and then it will be in saturation, and then it will be in linear region. So we can see here between 320 and 470, this NMOS is in saturation region. Okay, okay. Now, here is the difference between the amplifier with resistive load and with the current source load. So here we can see the variation of the output, like when transistor is in saturation, right? So here the output will be vary between VDD to Vin minus VTH1. This is the output voltage swing. Okay, we will see the we usually see the swing like one is full voltage like 0 to VDD, and one when both transistor will be in saturation. So we are going to operate as an amplifier when both will be in saturation. So we will going to see the output voltage swing when both transistor will be in saturation region, right? So here, as we moving from this resistive load to this current source load, as we can see here, the our swing is reduced. Like earlier, it was VDD and Vin minus VTH1 to VDD output swing was there. Now it is Vin minus VTH1 to VDD minus VD set of this M2. So we can see one disadvantage in this circuit compared to this is the swing is reduced. The output voltage swing is reduced. Right. So how we will find the gain? So here to find the gain, what we will see. So here, if from output side, if we see the upside, the resistance will be resistance will be R02, and if we see the input from output to downside, the resistance will be R01. So overall resistance equivalence resistance will be R01 parallel to R02. Okay, and the transconductance from this by changing input, the current will change, that is GM. Okay, so the gain will be minus GM time into R01 parallel to R02, and we can see this circuit is we have kept we have moved the circuit like a small signal model, and then we realize this circuit in a easy way here, right? Okay. Now we can see the common source with active load. So as we can see here, this is look like a inverter. Okay, this is a inverter, CMOS inverter. So yeah, we can use CMOS inverter also as amplifier, but this circuit has a major disadvantage. That's why we don't use this circuit as amplifier. Now what will we will see how this input output variation and what is the gain and what is the disadvantage of this circuit. So here, as you see the region of operation of M0 and the M1, we can see this NMOS is the M0 and PMOS is the M1. So we can see here the variation when we are varying this voltage VB, how this region of operation is going to affected. So we can see here both NMOS and PMOS will be in saturation when the voltage is between 380 to 430. So we can say that our input range will be how much? Input voltage range will be 380 to 430, because in this voltage only we are going to use this active common source stage with active load as a amplifier. So this is the input output characteristics. This is familiar to you since this is the CMOS inverter. uh, we know how this variation is going to happen, right? Okay. Okay, so what will be the gain of this circuit? If we do the small signal analysis, we will find, okay, the here, like see here, the current is gm2 v2 and gm1 v1. These two both current is contributing in the output voltage, right? So what the overall structure will be like this, and we can say like this: gm1 plus gm2 v in, this current is going through this load, and that is creating the output voltage. So we can say like this gain will be nothing but v out upon v in, and this will be minus gm1 plus gm2 into r01 parallel to r02. Now what is the drawback of this circuit? And the drawback of this circuit is like if uh, if there will be any noise present into the this VDD, our supply source supply. If there will be any noise, any small disturbance will be here, then this circuit is amplify that noise voltage, and this amplify that noise voltage and produce noise at the output. Like, so if any disturbance, any small disturbance at this supply, okay, this small disturbance will going to amplify and available at this V out. So we can see like here, uh, okay, so we can see like the circuit amplify the supply voltage variation in the VDD. Like, so if there will be any change here, it will be going to reflect here by the amount of gm2, okay, into r02, okay, plus 1 divided by r01 plus r02 into r01. Okay, so the major disadvantage of this circuit is it is going to amplify the noise that is present into the supply voltage. That's why we don't use this CMOS inverter as amplifier. Now, this is the last topic where we are going to use common source stage with source degeneration. Like, so what is the advantage of this circuit comparing to all? Okay, we will going to see how this circuit is going to linearize. Okay, the variation between this ID and the Vin. So here we can see like if our V in this voltage at the gate will increase, right? Okay, then our VGS will going to increase, correct? So when the voltage at the gate will increase, the current through the drain of this MOSFET is going to increase, and the same current is flowing through this resistor, okay, RSS. So voltage across this resistor RSS is going to increase. So as we can see here, by increasing this gate voltage, that VGS was going to increase, but it affect the current also, and current is increasing, and now the voltage at source is increasing, and because of this VGS is again going to decrease. So we can see like it is the negative feedback. As we are increasing VGS is increasing, and again because of current, this voltage at the source is increasing, and this going to normalize this VGS increase, right? So we can see like this circuit is behave more linearly compared to other circuit. Okay, so what I have told, the explanation of this is here. As Vn is increased, so do IID and voltage drop across RS, that is fraction of change in the Vn appear across the resistor rather than a gate and the source overdrive, thus leading to the smoother variation of the ID. Now we can see here V out is equal to VDD minus ID into RD. What will be the V out? V out will be equal to the VDD minus whatever the current flowing through the drain into this resistance. Right. Mhm. So yeah, now we are going to see the gain of this circuit. Like, so we are going to find the overall transconductance here and then output resistor. Okay, and then we are going to find the overall gain of the circuit. So we can see here what will be the transconductance. Transconductance will be nothing but the variation of current, derivative of the current in the drain to the derivative of the input voltage. Now gm will be the del id upon by del v in, and we can write this like this. Okay, del f by del vgs into del vgs by del v in. Just we divide and multiplied with del vgs. Now we can see here the vgs is nothing but the v in minus id into rs, and then del vgs will be 1 minus r S into del ID upon del V in. We are going to keep this here, and from here we can say our overall transconductance is nothing but Gm divided by 1 plus Gm Rs. Earlier in all the circuit we can see the transconductance is overall transconductance is Gm, but we observe here the overall transconductance is not Gm, right? It is Gm divided by 1 plus Gm into Rs. Now as we can see here, we can observe here overall transconductance is less dependent upon the Gm, right? Let me tell you here. One second. Okay, so here what will happen if 1 by sorry, if 1 second, let me erase this. Okay, we can see here if GMRS is here, we can see here GMRS is more than 1, right? So we can neglect 1 compared to GMRS. So overall transconductance is nothing but GM divided by Gm into Rs, that will be equal to 1 by Rs. So we can see here our overall transconductance is not depending upon the Gm, right? It is 1 divided by Rs. Okay, now what will be the gain? Gain will be the overall transconductance time, the output impedance, that is minus Gm into Rd. That will lead to minus Gm Rd divided by 1 plus Gm Rs. So if uh, here the GMRS is more greater than more than 1, so we will neglect this one compared to GMRS. So we will write minus GMRD divided by GMRS. So the overall gain will be minus RD by RS. So we can see here the gain is not depending upon the GM. The gain is depending upon the resistor, that is RD and RS. Okay, so we can say here as RS increase, the GM become a weaker function of the overall GM become the bigger function of transconductance and hence the current, right? So we will see how this if we are going to increase the V in. Okay, earlier with this is the result without source, without resistor at the source, and this is the result with resistor at a source. So without resistor at a source we can see here the variation of id with respect to V in. So here when Vin will be increased, our transistor earlier will be in cutoff region, then it will go move into the sub-threshold saturation, okay, near to this. Then it will go to the saturation region, and then it will move to the linear region. Now when we have applied this source resistor, we can see this idea is become more linear with V in, right? Here if you see this graph and this graph, we can say this RD become more linear with V in. And we can see finally the GM graph here, transconductance graph. Okay, now we are going to observe this in the tool how this is more linear. Okay, so we can see here the first graph is without RS and second one is with RS. So without RS we can see, and with RS we can see. With RS it's look like more linearized when we are increasing V in. Okay, the ID is more linear to V in. So this is the benefit of this circuit. And here we can see the region of operation of the NMOS, the NMOS in the saturation region between 330 millivolt to 740 millivolt. So we can use this as a amplifier between this voltage range. And this is the input output characteristics. We can see VI characteristics here. As Vin is increasing, our Vout is decreasing, right? And okay, that's all. I think I have covered all single stage uh, common source with a common source amplifier.